Welcome to Oceanic and Polar Experts. In this episode, we are very excited to feature an interview with a physical oceanographer, Professor Xiaozhou Ruan. He graduated from Ocean University of China, later earned a PhD at California Institute of Technology, Caltech, and did a postdoc at MIT. Now working at Boston University, Professor Ruan studies small-scale ocean dynamics and their roles in the large-scale coastal and global ocean circulation. More specifically, his research examines energetic submesoscale ocean currents, ranging from 100 meters to 10 kilometers in horizontal length. Boundary layers are usually tens of meters thick, and turbulent mixing events that extend from centimeters to meters. To approach these questions, Professor Ruan uses a combination of theoretical fluid dynamics, numerical modeling, and observational data analysis. As a professor, he also teaches a number of courses at Boston University, namely Introduction to Climate and Earth System Science, Introduction to Physical Oceanography, and Dynamical Oceanography. Today, he will share with us his research in small-scale ocean dynamics, an Antarctic trip he's been on, and his experiences at different institutions, Ocean University of China, Caltech, MIT, and Boston University. Join us for an enlightened conversation. Hi, Professor Ruan. Can you tell us a bit about yourself and what you do?
Sure. My name is Xiaozhou Ruan, born and raised in China. I came to the US to pursue a PhD after I got my undergraduate degree in China. I'm an oceanographer by training and I study ocean physics, basically the physics and geography of the ocean currents and the seawater properties. So you can really call me a physical oceanographer, which is different from, say, biological or chemical oceanographers who study biology or chemistry in the ocean. Currently, I'm an assistant professor in the Department of Earth and Environment at Boston University.
Why is it important to study ocean physics?
This is one of my favorite questions. The ocean acts as an important thermostat for the whole climate system. It is a huge reservoir for carbon and heat. Just to give you some numbers, the ocean stores more than 60 times more carbon than that in the atmosphere, and so far has absorbed more than 90% of the additional heat brought into the climate system by anthropogenic greenhouse gas emissions. So it's really crucial to understand how the carbon and heat is stored and redistributed in the global ocean. This relies on accurate understanding of how the ocean moves across a wide range of spatial and temporal scales. And this is what we do as oceanographers. And oceanographers and climate scientists worry that the heat and carbon currently stored in the ocean may eventually resurface and be released back into the atmosphere. That would be catastrophic, right? So it is our job to understand how the seawater moves so that we can better predict how the ocean affects future climate.
Your current research focus is on small-scale ocean physics, and you said that they are challenging to resolve for traditional observational and computational approaches on your website. Why is it, and how do you approach this?
This is a very good question. Oceanographers typically use two popular approaches to study the ocean: observations and building mathematical models to simulate ocean processes on computers. Observations require significant efforts and time to make measurements in the ocean. The traditional approach involves stopping a ship at predetermined stations to measure vertical profiles of current speeds and seawater properties such as temperature and salinity. However, the more stations we stop at, the more time it takes, which would limit the area we can cover, since very often the ship time is very limited. As a result, we often take measurements at stations tens of kilometers apart, which means we will miss small-scale ocean features. The computational approach involves dividing the whole global ocean into millions of small boxes, where fluid mechanics are simulated over time. This is similar to how a camera lens works. The more boxes you have, the higher the resolution and the more physics you can resolve in the numerical models. Unfortunately, we are also limited by computational power and thus must use a finite number of boxes. In a typical global climate model, the size of each box can be hundreds of kilometers. With such coarse resolutions, many small-scale ocean processes are missing in the simulations. So this is why small-scale ocean physics are really challenging to resolve for traditional observational and computational approaches. That said, we are making significant efforts to study the small-scale ocean physics because they have proven to be really crucial for the whole global ocean system. Oceanographers have started using ocean robots that can be deployed for several months to take continuous measurements. This advancement allows us to gather an unprecedented number of measurements, which allows us for a better understanding of the small-scale ocean physics that were previously missing. For computational models, what we do is design simulations that specifically target the small-scale ocean physics. Due to the computing power limitations, this high-resolution approach means our domain cannot be very large. Once we gain a better understanding of how the small-scale ocean processes work, we often develop the so-called parameterizations to represent the effects of these processes based on the output of coarse-resolution ocean states. Finally, we incorporate these parameterizations back into the coarse-resolution global climate models to achieve a more accurate representation of ocean dynamics within the climate system.
I know that you've been to the Antarctic. That's so cool. Can you tell us more about it?
Of course. The goal of the Antarctic cruises is to deploy ocean robots to monitor the processes by which heat is delivered across the Antarctic continental margins, contributing to the melting of ice sheets, ice shelves, and glaciers. This is another popular topic of oceanography research, specifically the impact of melting land-based ice on global sea level rise. We began our journey from Chile, crossed the Drake Passage, and cruised around various glaciers and ice sheets in the Southern Ocean, taking measurements from the ship and with the robots.
What is the most exciting part of your trip?
Well, I have to say that the whole trip was very exciting and memorable. And of course, the most exciting part is that we managed to obtain a lot of data from our measurements. This allows us to take a detailed look at the processes occurring near Antarctica. We know that the ocean is stratified in most cases, typically with denser water below lighter water. One of our robots actually detected an exceptionally thick layer, around 200 meters thick, with almost the same density. So this thick layer sits at the seafloor in a water column about 1,000 meters deep. This is the first time such thick, homogeneous layers have been observed near Antarctica, and it indicates there's very active mixing processes that are happening near the seafloor that are mixing together waters of different densities. This exciting dataset provides us with a very rare opportunity to study and interpret the processes occurring in the deep ocean in this region. Personally, I was also excited to see so much amazing wildlife, including whales and penguins. We even docked at one of the US Antarctic stations, where I took the plunge into the ice water, which was super fun and incredibly cold.
You've studied at Ocean University of China, Caltech, and did a postdoc at MIT, and now are a faculty at Boston University. How did you find your experiences? Did you find any differences between these institutions?
Yeah, it's been a very fun experience for me personally, having the opportunity to study and work at these schools. These schools are obviously very different. You have a typical public university in China, two relatively small institutions in the US with a lot of emphasis on science and technology, and Boston University is obviously a bigger school with a lot of majors other than science and technology. For instance, we have law school, journalism major, and performing arts major, etc. Throughout these transitions, my personal roles have also evolved from being an undergraduate to a graduate student then to a postdoctoral researcher after earning my PhD, and finally to becoming a professor. I've enjoyed every step of the journey so far.
Some people say Caltech and MIT are alike in some ways. In your mind, how are they different and how are they alike?
Well, I can only comment on these two schools based on my personal experience in the Earth department. Also, you have to consider the fact that I was a student at Caltech, but a researcher at MIT, so I didn't really take many courses at MIT. I can say that there is definitely a lot more similarities than differences between the two schools. In terms of the similarity, you can already tell from their names that they both focus a lot on STEM. In fact, there's a lot of collaboration between the faculties at the two schools. They are also quite different in several ways. The most noticeable difference to me is the weather. Caltech is in Southern California, so much more sunshine, while you get a lot more snow at MIT. The size of the two schools is also quite different. Caltech is much smaller than MIT, which allows students to benefit somewhat from the smaller class sizes and perhaps more personal attention from their professors. That said, if you get accepted to both schools, you can't go wrong with either option.
Among all those institutions we talked about, which one is your favorite?
My personal favorite is Caltech, simply because of the weather. You just can't beat the weather in Southern California.
Very true. How do you find teaching students oceanography at Boston University?
I have to say I didn't expect it to be so much fun. This past spring, I taught a large freshman class called Introduction to Climate and Earth System Science. As I mentioned earlier, there are many non-STEM students at Boston University, so I got to teach earth science, including oceanography, to students majoring in, say, journalism and anthropology. This might be their only opportunity to learn something systematic about the Earth and the ocean. I prepared some really cool earth science stories and examples, and I could tell the students were genuinely excited and intrigued. It was a really fulfilling experience for me.
Do you have any advice for those interested in your field?
Yes, here are a few pieces of advice I can give. Number 1, build a strong foundation in STEM. A solid background in science, technology, engineering, and math is essential. Courses in physics, math, and computer science are particularly important. Number 2, learn to code. Proficiency in programming languages like Python, MATLAB, Julia, or R is crucial. Many oceanography models and data analysis tools rely heavily on coding. Number 3, stay curious and keep learning. The field of oceanography is young and is constantly evolving. You need to stay updated with the latest research from different news outlets, etc. Number 4, get hands-on experience. Engage in internships, research projects, or fieldwork opportunities. In the US, there are many opportunities or programs for high school students to engage in research with university faculty members, and I'm sure there are similar programs you can find in the UK. Number 5, focus on interdisciplinary knowledge. Oceanography often intersects with other fields like meteorology, climate science, and environmental science. A broad understanding of related disciplines can provide valuable context and insights.
What are some important skills needed for this field?
Math, physics, and coding, as well as strong communication skills. Math, physics, and coding are the foundations. Being able to effectively communicate your research to fellow scientists and convey your ideas to the general public is also crucial. I think these are all the important skills you will need.